5.48 milliarcseconds. That is the angle UY Scuti occupies across the sky, a measure so small that the unaided eye cannot begin to approach it, smaller than the gap between two paint molecules on a printed page held at arm's length, smaller than anything the naked eye could ever resolve into a shape or a disk, or even a suggestion of one. To every person who has ever stood outside at night and looked up, UY Scuti is a point. It is a pinprick. It is indistinguishable from the 1,000 other points scattered across the same patch of sky in Scutum the Shield constellation, low above the southern horizon on summer nights. And yet, if UY Scuti replaced the sun at the center of the solar system, its surface, the glowing, churning, diffuse boundary where its light finally escapes into open space, would lie somewhere near the orbit of Jupiter, not near the orbit of Earth, not somewhere between Earth and Mars, near Jupiter. Every planet inward from there. Mars, Earth, Venus, Mercury would be inside the star, not orbiting it, inside it, buried within the glowing interior of a body so vast that the distance from its center to the surface of its photosphere spans the entire inner solar system and then reaches outward past the asteroid belt, past everything. That star appears as a point of light, no different from any other. The numbers involved are almost too large to move through comfortably, so it helps to begin at a smaller rung. The sun, by any ordinary measure, is itself enormous. Its radius, the distance from its center to the visible surface, runs to approximately 695,000 kilometers. From one side to the other, it spans a distance that light crosses in just over 4 seconds. To cross it the long way, end to end, takes about 4.5 seconds of travel at the fastest speed anything in the universe can reach. The Earth, by comparison, is roughly 109 times smaller across, a marble beside a basketball, as comparisons of this kind tend to go, though even that image does not fully land. 109 Earths arranged edge to edge would reach from one side of the sun to the other. That is the unit. That solar radius, those 695,000 kilometers, is the ruler against which all other stellar sizes are measured across every branch of astronomy that concerns itself with how large stars are. It is the standard, the baseline, the familiar rung on the ladder. UY Scuti has a radius of approximately 1,708 of those units. 1,708 solar radii. That is the measurement produced when astronomers using the Very Large Telescope Interferometer in northern Chile combined the light from widely separated instruments to produce enough angular resolution to say something meaningful about a star that subtends only 5.48 milliarcseconds in the sky. Even then, the estimate carries uncertainty. Even then, the number is approximate. But 1,708 solar radii is a figure that, once it settles in, does not easily settle back out. 1,708 solar radii means that if the sun were the size of a golf ball, UY Scuti would be roughly the height of a 2-story building. It means that light, traveling at the speed it always travels, would take more than 14 seconds to cross from one side of UY Scuti to the other. It means that the volume of this star is so much larger than the volume of the sun that expressing the ratio requires numbers most people never encounter outside of scientific notation. The sun, placed inside UY Scuti, would rattle around like a seed inside a hollow building, and UY Scuti is not even the largest known star. Stephenson 2-18 carries an estimated radius of approximately 2,150 solar radii. The number is uncertain. Stellar size estimates for the most extreme objects always carry significant uncertainty, for reasons that will make themselves clear, but 2150 is the figure the best current measurements suggest. At that size, if it replaced the Sun, its photosphere would extend beyond the orbit of Saturn, not to Saturn's distance, past it. Saturn itself would drift in the interior of the star, along with Jupiter and every planet between them and the Sun itself and the entire space those planets have moved through for the past 4.5 billion years. All of it. All of that space, all of those orbits, all of those distances that ancient astronomers once thought defined the boundary of the known universe inside the star, between Saturn and that star's surface. At that scale, there would be nothing, no boundary to cross, only the interior. It is useful, when a scale this large resists being held as a number, to let it become a place instead. Stand somewhere on a surface in the solar system as it currently exists, say the rocky surface of one of the small moons of Mars, where the sky above is black and the Sun appears smaller than the moon appears from Earth. Now replace the Sun with Stephenson 218. The sky does not fill with a larger sun. The sky becomes the star. Every direction from that surface looks into the interior of a star, not toward it. The light comes not from a disk in the sky, but from all directions at once, an infinite enclosure of glowing material, with no horizon that leads anywhere else, because everywhere leads inward. This is not an approximation for dramatic effect. This is the geometry. A solar radius, 695,000 kilometers. It is worth staying with that unit for a moment, because the way stellar astronomers use it is both technically precise and practically necessary. It is the standard because the Sun is the star we know most thoroughly, the one whose surface we have photographed, whose atmosphere we have probed, whose interior structure we have mapped by measuring the way sound waves cross it from side to side. Everything else is calibrated against what we know about the Sun. When a paper reports that a particular red supergiant has a radius of 900 solar radii, the reader has an anchor, 900 times the distance from the center of the Sun to its visible surface. The number holds meaning because the reference is stable, but the reference is already enormous, and the stars at the upper end of the size distribution reach radii that dwarf even the most generous comparison. Between the radius of the Sun and the radius of Stephenson, 2 minus 18, the ratio is so extreme that it begins to feel almost unreasonable. It almost seems as though something should have prevented this, some physical process, some law of structure, some limit. And indeed, limits exist, but within them, stars of this size are real, measured, observed. Their distances have been calculated. Their light has been parsed into spectra. Their angular diameters have been extracted from interferometric data. They exist. The technique that allows that extraction is one of the quieter triumphs of modern observational astronomy. A single telescope, no matter how large, cannot resolve the angular diameter of a red supergiant at thousands of light-years distance from Earth. The disk is simply too small. 5 milliarcseconds is smaller than the best angular resolution any single optical telescope can reach, no matter the aperture. To see a disk where there appears only a point, astronomers combine the light from 2 or more telescopes separated by some large physical distance, tens or hundreds of meters, and use the interference patterns between those signals to reconstruct information about the source's angular size. The wider the separation between the telescopes, the finer the angular detail the combined system can resolve. This is the principle behind the Very Large Telescope Interferometer in Chile's Atacama Desert, where the 2013 measurements of UY Scuti were made by a team including researchers working under the name Arroyo Torres. The result was a number, 5.48 milliarc seconds, and from that number, combined with an estimate of the star's distance, which is itself a quantity carrying its own uncertainty, came the radius, approximately 1708 solar radii. A point of light in the constellation Scutum, unremarkable to the eye, resolved by an array of telescopes into a star that could swallow the inner solar system without disturbing the orbit of Jupiter. Distance estimates carry their uncertainties forward into size estimates, and this is worth understanding as a quiet background fact rather than a problem. For stars measured by the Hipparcos satellite and later by Gaia, parallax measurements give distances with precision that was unimaginable before those missions. For more distant stars, or stars embedded in dusty, complex regions, the distance remains harder to pin down. A 10% change in the estimated distance of UY Scuti carries forward into a 10% change in the estimated linear radius. 1708 solar radii might be 1500, it might be 1900. The uncertainty is not the kind that throws the picture into doubt. A star somewhere around 1700 solar radii is still a star that would engulf the inner solar system, but it is the kind that makes the extreme end of any size ranking provisional, subject to revision as measurements improve. Around the largest red supergiants, this uncertainty is made more complicated by the presence of circumstellar dust. Many of the most enormous cool stars lose mass in vast, slow outflows, material ejected from the surface over long periods, drifting outward through the surrounding space. As that material cools, it forms shells of dust, and those shells glow at infrared wavelengths that the human eye cannot see. When an interferometer observes such a star at different wavelengths, it measures different apparent sizes. At one infrared wavelength, it may be resolving the inner boundary of a dust shell. At another, it may be resolving the outer edge of the stellar atmosphere. In the optical, it resolves something closer to the star's actual photosphere. None of these measurements is wrong. They are measuring different things. VY Canis Majoris, one of the most studied examples of this kind of star, is surrounded by an intricate structure of circumstellar material, arcs, knots, fans of gas and dust ejected over centuries, glowing warmly in the infrared at distances that extend well beyond the star itself. The dust has been pushed outward by the stellar wind, moving at tens of kilometers per second, accumulating at distances where it can cool and condense and glow. When any measurement of this star's angular diameter is made, the question of what exactly is being measured matters. The photosphere is in one place. The inner dust envelope is somewhat larger. The outer extent of the circumstellar material larger still. Depending on which feature an observation resolves, the reported size of the star can vary by tens to hundreds of solar radii. This is not a failure of measurement. It is an accurate report of a genuinely complex object, one whose boundary is not a simple line. The photosphere of the sun, as understood in solar physics, is the layer where the optical depth reaches a value close to 2/3, meaning, in physical terms, that this is the depth from which a photon has a reasonable probability of escaping outward into space, rather than being absorbed and re-emitted again by the surrounding gas. Below this layer, the stellar interior is opaque. Above it, the gas thins enough that light travels freely. The photosphere is therefore the boundary from which the star's visible light is most directly emitted. the layer most closely associated with the star's color and its measured temperature. For the Sun, this boundary is relatively well defined. It is still not a sharp line in the way a solid surface is a sharp line. It is a zone, a few hundred kilometers thick, in a star whose radius runs to nearly 700,000 kilometers, which makes it thin enough to be treated as a surface in most practical contexts. What lies above it, the chromosphere, the corona, is genuinely part of the Sun, but it is tenuous, hot, and transparent, extending outward in the form of the solar wind until it merges with the interplanetary medium. In a red supergiant, the photosphere is a far more extended and diffuse structure. The star's surface gravity is low, enormously low compared to the Sun, because although the star is far more massive than the Sun, its radius is so much larger that the gravitational acceleration at the surface is reduced to a small fraction of what it is at the solar surface. In low surface gravity, the stellar atmosphere puffs outward. The gas that would be packed into a thin boundary in a more compact star spreads itself over a much larger volume, and the transition from opaque interior to transparent atmosphere becomes correspondingly broad. The photosphere of a red supergiant is not, in any meaningful physical sense, a surface. It is a zone. It is a region of transition, a gradient from dense to thin, from opaque to transparent, from hot interior to cool outer layers, across which the definition of where the star ends becomes less and less precise. In some models of red supergiant atmospheres, this transition zone extends over hundreds of solar radii. The star does not end where the light comes from. It continues outward, growing thinner, cooler, more tenuous, until at some uncertain distance, its material merges with the circumstellar dust and the surrounding interstellar medium. Where a star ends is not a question with a clean answer. This diffuse quality of the red supergiant surface is part of what makes these objects so difficult to characterize precisely, and also part of what makes them so unlike any intuitive sense of what a surface should be. Imagine standing, if the word standing retains any meaning in such a context, at some point within the outermost layers of a star, like UY Scuti, in the region that the models define as its photosphere. The temperature around this region runs to somewhere between 3,500 and 4,500 Kelvin, hot enough that everything is gas, that no solid or liquid matter could survive, that the atoms of every element present are in various states of ionization. The light in every direction is intense beyond anything the human eye is built to endure. But the gas itself is, in terms of density, extraordinarily thin, thin enough that the photosphere of a red supergiant is in some ways closer in density to the best vacuum achievable in a laboratory on Earth than it is to the kind of gas found in a room at ordinary conditions. A red supergiant is enormous and luminous and glowing, but it is not dense in the way everyday experience of physical objects suggests. It is something more like a vast, slowly churning, gently luminous cloud, loosely bounded, its edges dissolving outward into space. The dust shells that surround these stars form from that outward moving material. When the gas expelled from the photosphere travels far enough from the star to cool, when the temperature drops below roughly the point where silicate minerals can condense from gaseous atoms into solid grains, the first particles of dust form. They are tiny, measured in fractions of a micrometer, but they are opaque at optical wavelengths, and they absorb and re-emit starlight in the infrared. The warm halos that result from this process glow at wavelengths the human eye cannot detect, invisible to anyone standing outside on a clear night and looking up, but bright to instruments tuned to the right frequencies. Around VY Canis Majoris, the circumstellar material is complex enough to have been mapped in some detail. There are arcs and loops. There are regions where mass loss appears to have been concentrated in particular directions or at particular times in the star's history. There are structures that suggest the star has gone through episodes of especially intense ejection, followed by periods of relative calm. The whole arrangement drifts outward at tens of kilometers per second. In the scale of human time, this is fast. In the scale of stellar evolution, it is glacial. The material expelled from VY Canis Majoris in a year covers a distance tiny compared to the star's own radius. It will take thousands of years for the inner dust envelope to reach the distance from the star that the outer envelope has already reached. Meanwhile, the star continues to glow at the center of all of it, cooling and vast and diffuse at its edges, and the dust drifts. The angular size of a star, measured by an interferometer, depends on which of these layers the observation happens to be sensitive to. At a mid-infrared wavelength, the observation may be dominated by the emission from warm dust, and the apparent diameter includes a large contribution from material that is not really the star's photosphere at all. At shorter wavelengths in the near-infrared, the measurement comes closer to the extended stellar atmosphere. In the optical, where the dust is more opaque, but the stellar photosphere emits less, the measurement is sensitive to slightly different parts of the atmosphere. Again, each wavelength gives a number. Each number is real. Together they describe an object that occupies multiple spatial scales, whose boundary is not fixed, whose edge depends on the question being asked. This is not a problem unique to the very largest stars, but it is most acute there. A smaller, hotter star, a blue-white giant, for instance, or a main sequence star like the Sun, has a much higher surface gravity, a thinner and more well-defined photosphere, and typically produces far less circumstellar dust because its wind is driven by radiation pressure on the gas rather than on dust grains. The compact, definable boundary of a hotter star is partly a consequence of the same physics that makes it compact. The cool red giant, with its low surface gravity and slow dusty wind and thick extended atmosphere, is in some fundamental sense an object that resists being measured in the same way. And so the largest known stars carry their uncertainties with them. 1,708 solar radii for UY Scuti, measured with as much precision as the technique and the distance estimate allow, reported carefully, understood to be the best figure available. 2,150 solar radii for Stephenson 218, a number that places its edge past Saturn's orbit, derived from observations that include all the complications of atmosphere and dust and distance and wavelength. The numbers are not exact, the stars are not precisely defined, and in this, the stars are being accurately described. The universe contains objects that resist the categories we build for them. A star that extends its atmosphere over a region larger than the inner solar system does not have an edge so much as a gradual fading. It glows most brightly near its center and grows dimmer, thinner, more uncertain as the distance from the center grows. Out at the far reaches of the circumstellar dust shell, a light week from the photosphere perhaps, or a light month, the material that was once part of the star's surface drifts in the dark. It is no longer emitting the star's light. It is reflecting and re-emitting a faint share of it, in the infrared, invisible to unaided eyes. And inward from there, the gradation continues. Gas thins to an atmosphere. Atmosphere thins to a photosphere. Photosphere thickens inward to become the stellar interior. There is no line, there is a continuum. To look at UY Scuti from outside the solar system with the naked eye would be to see a point of faint red light. To resolve it at all with a single optical telescope would be to see only a point, regardless of the telescope's size, because the angular diameter is simply too small. Only by combining light from widely separated instruments, by building a baseline across tens or hundreds of meters of physical distance, and by measuring the way the combined signal changes as the separation is varied, can any information about the disk be extracted. The resulting measurement is a number, 5.48 milliarcseconds, and from that number a radius, and from that radius an image of something so large that the solar system's inner half fits inside it. All of that from a point of light that looks like any other. The distance from the Sun to Saturn is a vast span by any measure tied to human experience. On the scale at which people moved through the world for most of human history, on foot, by horse, by sail, the distance to Saturn is effectively infinite. Even today, a spacecraft takes years to cross it. The Voyager probes, launched in the late 1970s, reached the vicinity of Saturn only in 1980 and 1981 after years of travel. The distance they crossed is the distance to a planet that Stephenson 2.18's surface, if placed at the Sun's location, would surpass that distance. All of that travel, all of those years, and still inside the star. The natural tendency, when numbers of this kind appear, is to reach for an adjective, to call the scale incomprehensible, or humbling, or any of the words that serve as placeholders for a size that exceeds easy imagination. The better tendency is to stay with the number a little longer. 1,708 solar radii, 2,150 solar radii. These are the measured, estimated sizes of real objects in the galaxy. They are not metaphors, they are not similes. They are descriptions of structures that formed from gas, that undergo nuclear reactions in their interiors, that lose mass to slow stellar winds, that may one day collapse and explode, and scatter their material across the surrounding interstellar medium. They exist. They glow. From Earth, they appear as points. There is something in that contrast, the immensity contained within the point, that the mind can rest against without needing to fully resolve it. A point of light, faint, red, unremarkable in its patch of sky. And within it, or behind it, or described by the angle it subtends across the dark, something that the inner solar system fits inside. The mind holds both facts, the point and the volume, the visible and the inferred. The photosphere itself is worth returning to, in closing, because in a red supergiant, the question of where the visible light comes from is genuinely less settled than it might seem. The optical depth condition, the criterion of 2/3 that defines, in the more compact and well-studied case of the Sun, the specific layer from which light most freely escapes, still applies in principle. But in the extended, low-gravity, slow-moving atmosphere of a red supergiant, the region satisfying that condition is spread across a thickness that would be substantial even by planetary standards. The photosphere is a zone that extends, in some models, over 100 or more solar radii. Its inner and outer edges blur into adjacent regions by degrees rather than sharply, and beyond the photosphere, as the gas continues to thin outward, there is no clean boundary. There is material, increasingly sparse, increasingly cool, drifting away from the stellar surface on the slow current of the stellar wind. There is dust condensing where the temperature drops low enough to allow it. There are shells of that dust glowing in the infrared at distances that expand with each passing century. There is, at some point, a gradation into the surrounding interstellar medium, the thin gas that fills the space between stars, a transition so gradual that drawing a line across it would be an act of convenience, not an accurate description of any physical edge. The largest known stars have no clean edge. They thin, they cool, they extend their material outward into the surrounding dark in slow, warm halos of ejected gas and dust, and those halos drift, and the dust within them drifts a little faster at the outer boundary, where the wind has been pushing it longer, and at no point does anything snap cleanly closed into a surface, the way a moon or a rock or a pool of water does. A star this size ends the way a fog ends, not at a line, but at a distance, at a gradual thinning, at the point where the light reaching an observer has been sufficiently scattered and absorbed and redirected that it tells a different story. Out there, beyond the measured disk, beyond the dust shell's inner edge, the material that left the photosphere some thousands of years ago continues its slow outward journey. It carries within it the chemical signature of the star's interior, elements processed through long nuclear burning, expelled into space, eventually to mix with the surrounding medium and become part of the raw material from which future generations of stars and planets will form. But that is far from the photosphere, and far from the point of light visible in the night sky, and far from the number 5.48 milliarc seconds that, when turned carefully by the right instruments into a radius and then a scale, reveals within a single unremarkable point of red light, a space the solar system fits inside of without filling. The star does not have a clean edge. That is, in the end, perhaps the most honest thing that can be said about it. Its boundary dissolves outward, gradually into dust and gas, and the cooling remnants of what was once the stellar surface, without ever arriving at a definite end. Something that vast and that diffuse does not resolve into a line. It resolves into a gradient, a long, slow dimming from the dense luminous interior to the thin outer atmosphere, to the warm infrared glow of the circumstellar dust, to eventually the quiet dark of the space between stars. The largest things resist being defined precisely. They extend themselves slowly and without hurry into the surrounding space, and their boundaries are not lines but distances, not surfaces but transitions, not edges but the gradual place where the star becomes something else. Atmosphere, wind, dust, dark, without any single moment when the change is complete. Somewhere in the plane of the galaxy, far from any sun, a cloud of gas and dust hangs in the dark. It is not moving, or it seems not to be. It has been here for a very long time, longer than the solar system has existed, longer than the Earth has had oceans, drifting slowly through the outer arm of a spiral, cold beyond the reach of any nearby warmth. The temperature inside it is only a few degrees above the lowest temperature anything in the universe can reach. At that cold, molecules barely move. Hydrogen pairs into quiet dimers. Carbon monoxide forms and holds its shape for millions of years without breaking. The cloud has mass enough to make thousands of suns, and it is doing nothing with it yet. That stillness will not last. It is already ending, in ways too slow for any single observer to watch. A faint filament inside the cloud is a little denser than the rest. Where there is density, there is slightly more gravity. Where there is slightly more gravity, more gas drifts inward, so slowly that the drift is measured not in years, but in tens of thousands of them. The cloud is beginning in the way that glaciers begin, in the way that mountain ranges begin. The first cause is gravity, and gravity is patient beyond any scale the human life can hold. The cloud spans something like 200 light years from edge to edge. A beam of light, the fastest thing there is, would take 2 centuries just to cross it. Inside that enormous cold volume, the gas is not smooth. It is clumped and threaded, crossed by filaments and voids, shaped by ancient turbulence left over from shock waves that passed through millennia ago. A nearby star may have ended its life in a great outward explosion, and the wave of that pressure is still moving through the cloud, still compressing filaments, still tipping the balance of forces in pockets too small to see from the outside. The shock wave gave the cloud a push, and the cloud is still responding. Gravity and pressure have been arguing here for a very long time. Thermal pressure, the outward push of gas that is even a few degrees above nothing, resists collapse. Magnetic fields threaded through the cloud push back against compression, stiffening the gas the way a wire mesh stiffens a structure. Turbulence, the slow churning of a cold gas too massive to settle, provides another kind of resistance. Random and complex, different in every pocket of the cloud. For a long time, the argument is even. The cloud drifts on without collapsing. There is a threshold, though. When a region of gas becomes dense enough, massive enough, cold enough, gravity tips the balance past recovery. The thermal pressure is no longer sufficient to hold the region up. The magnetic field begins to leak as ions and neutral atoms slowly decouple, reducing the field's grip. The turbulent support fluctuates, and in one fluctuation, it is simply not enough. The region begins to fall inward, not quickly, not with any sound or light or drama visible at a distance. It simply begins to contract, the way breath leaves the lungs when the body finally rests. This is the beginning of a star. The quantity that describes this threshold is called the Jeans mass, the minimum mass at which a gas region's self-gravity can overcome its own thermal and turbulent resistance and begin a collapse that will not reverse. At the temperatures and densities of a giant molecular cloud, the Jeans mass is roughly 10 to a few tens of solar masses for a single condensation, though the details depend on local conditions that vary across the cloud's enormous interior. In some regions, the collapse breaks into smaller pieces. In the densest, most turbulent cores, where gas is funneled along filaments and compressed from multiple directions, something larger accumulates. A massive star begins here, in one of those dense cores. The core that will eventually produce a star of 60 or 100 solar masses is not initially that massive. It is a condensation, a knot of denser gas, threading inward along filaments, accumulating from the cloud around it, the way silt accumulates on a riverbed where the current slows. Material falls toward the center along the lines of the magnetic field, along the direction of turbulent infall, channeled and gathered over hundreds of thousands of years. Deep inside the collapsing core, a protostar forms, an object that is not yet a star, not yet hot enough at its center to sustain nuclear fusion, but already dense enough that infalling gas bounces against it and begins to heat. The protostar glows, but not in any light the human eye would see. It radiates an infrared, long, warm wavelengths that carry heat, but not the blue-white brilliance of stellar fusion. The surrounding dust absorbs the shorter wavelengths and re-emits them even further into the infrared, wrapping the young object in a warm glow invisible from any ordinary perspective. The protostar is buried. It will stay buried for a long time. From outside the cloud, there is no visible light. Only an infrared telescope, sensitive to the gentle warmth leaking through the dust, can find it. To build a massive star, the protostar must continue to accrete, must continue to gather mass from the surrounding gas at a very high rate and for a very long time. The rate required is roughly 1,000th of a solar mass every year. That sounds modest, but sustained across 100,000 years, it accumulates enough material to build a star of substantial mass. The difficulty is not the rate itself, but what the protostar begins to do as it grows. As its interior heats and its mass increases, it begins to radiate more intensely. The radiation pushes outward on the infalling gas, exerting pressure that resists further accretion. For a low-mass star forming in a quiet part of a cloud, this radiation pressure is not enough to halt accretion entirely. For a high-mass protostar, the outward push of its own light begins to rival the inward pull of gravity on the gas trying to fall in. The model that best accounts for how very massive stars manage to form despite this difficulty centers on turbulence. In a turbulent core, the gas is not falling in smoothly and symmetrically from all directions. It is disordered, channeled, asymmetric. Dense flows arrive along filaments and streams, concentrated enough in their own right to punch through the outward radiation pressure in a way that a diffuse uniform infall could not. The light escapes along directions of lower density, outward through the poles of an emerging disk, perhaps, while the denser equatorial infall continues. The protostar grows in fits and starts, fed unevenly, its growth not smooth but turbulent and episodic, punctuated by outflows and jets that carry away angular momentum and allow the disk to continue feeding the central object. This is not an easy process. It is not a clean one, but it works, and at the end of it, there is a massive star. When enough mass has accumulated and the core has compressed enough, the temperature at the center reaches somewhere around 10 million degrees. At that temperature, the first nuclear reactions ignite. Protons begin to fuse. The energy released by those first fusions heats the core further, and the reactions accelerate, and within a very short time, astronomically speaking, the star has found a new equilibrium. Outward pressure from the energy of nuclear fusion exactly balances the inward pull of gravity. The star has arrived on the main sequence, the long stable phase, in which it will spend most of its life. For a star of low or moderate mass, the main sequence is an era lasting billions of years. The Sun has already spent nearly 5 billion years in this stable phase, and it has several billion more ahead of it. For a massive star, the situation is entirely different. The most massive stars exhaust their core hydrogen in only a few million years, sometimes only 1 or 2. The reason is not simply that they have more fuel to burn, though they do. It is that their cores are so much hotter and denser that the reactions run at a ferocious rate. They do not merely burn hydrogen, they consume it. The fuel that would sustain a sun-like star for billions of years is gone in what amounts, on cosmic timescales, to an instant. The mechanism by which massive stars burn their hydrogen is also different from the mechanism operating in the Sun. In the Sun's core, hydrogen fusion proceeds primarily through the proton-proton chain, a direct collision process between individual protons. In a massive star, the temperatures are far higher, between 30 and 50 million degrees in the core, compared to 15 million in the Sun. At those temperatures, a different process takes over, one that uses carbon, nitrogen, and oxygen as catalysts. A carbon nucleus absorbs a proton, becomes nitrogen, absorbs another, becomes oxygen, then releases a helium nucleus, and returns to carbon, ready to absorb again. The carbon is not consumed. It acts as a middleman, passing through a cycle and emerging unchanged at the other end, while 4 hydrogen nuclei have been converted into 1 helium nucleus, and a great deal of energy. This is the CNO cycle, and in a massive star, it is the dominant energy source, running at temperatures the Sun's core never reaches, producing light equivalent to hundreds of thousands of suns, from a volume smaller than the distance between Earth and the Sun. That light is extravagant. It is genuinely structurally excessive, the star produces far more energy per unit of time than is strictly required to hold it up against gravity. The excess is not wasted. It drives the stellar wind, heats the surrounding nebula, ionizes the cloud the star was born in. But inside the star, it creates a condition of enormous internal pressure. The radiation itself contributes to holding the star up. In the most massive stars, the light accounts for more than half of the total internal pressure, supporting the structure against collapse. The star is held up, in significant part, by its own brilliance. This is a delicate arrangement, and one that grows more delicate as the star grows more luminous. The main sequence phase ends when the hydrogen in the core is exhausted. The core has been turning hydrogen into helium for millions of years, and now it has run out of hydrogen to fuse. Without a new energy source, the core can no longer produce the pressure needed to hold itself up. It begins to contract, slowly at first, then faster as gravity finds less resistance. The core is not cold. It is still immensely hot, and the contraction releases gravitational potential energy that heats it further. But for a time, it is not generating new energy through nuclear reactions. It is simply compressing. Something interesting happens to the outer layers of the star while the core is contracting. The energy from the contracting core flows outward into the star's envelope, and the envelope absorbs it. The envelope heats up, and as it heats, it expands. The expansion is gradual, covering tens of thousands of years, but it is enormous in its ultimate scale. What was a compact, intensely hot star begins to swell outward, its radius growing by a factor of tens, then hundreds, as the envelope pushes steadily outward against the diminishing resistance of gravity at those greater distances. As the envelope expands, it cools. A gas expanding outward loses temperature, the same principle that makes an aerosol feel cold as it sprays, that makes the upper atmosphere cold despite being closer to the sun. The outer surface of the expanding star drops from the fierce blue-white of the main sequence, where temperatures might have been 30,000 or 40,000 degrees, down through yellow, then orange, then the deep cool red of a surface at 3,000 or 4,000 degrees. The star is crossing the Hertzsprung-Russell diagram, that map of stellar temperatures and luminosities on which every star occupies a position determined by its physics. The crossing takes the star from the upper left, hot and compact, to the upper right, where the largest and coolest supergiants reside. This crossing is not instantaneous. It takes tens of thousands of years. During that time, the star occupies positions on the diagram that correspond to intermediate temperatures, the yellow and orange supergiants, categories rarely populated because massive stars tend to pass through them relatively quickly on their way to the cooler red supergiant phase. The star does not stop in these intermediate states unless some other physics intervenes. It tends to drift steadily rightward, cooling and expanding until it reaches the region where red supergiants live. At the cool end of this evolution, a constraint comes into play that is worth pausing on. There is a temperature below which a star of a given luminosity cannot maintain stable equilibrium. Below this temperature, the star cannot support its own structure using standard internal energy transport. The physics behind this limit involves the condition of full convection, when the envelope is so cool and opaque that energy must be carried outward by the slow churning of material rather than by the travel of radiation, and when this convection extends all the way through the envelope. In this condition, a minimum temperature for equilibrium emerges, set by the star's luminosity and composition. A star cannot cool its surface below this temperature and remain in hydrostatic balance. If it tries, it becomes unstable. This minimum temperature boundary is called the Hayashi limit, and it appears on the Hertzsprung-Russell diagram as a roughly vertical line near the cool right edge of the region where stars can stably exist. To the left of this line, stars of various temperatures and luminosities can maintain themselves in equilibrium. To the right of it, there is no stable configuration. The physics of convective envelopes simply cannot support a stellar structure below that temperature. Red supergiants gather at the left edge of this forbidden zone. They are as cool as they can stably be. Their surfaces hover at the margin of what is possible, their deep convective envelopes, transporting energy outward in vast, slow-churning cells that push the surface temperature as low as it can go without crossing into instability. The Hayashi limit sits in the diagram, not like a wall, but like a quiet edge, invisible, structural, a property of physics rather than a feature of any particular star. No red supergiant can push past it. They pile up against it, hovering in the few thousand degrees of temperature that the limit allows, their luminosities spanning a wide range, but their surface temperatures confined to a narrow band. The most massive and most luminous sit at the top of this band. The less massive sit lower. All of them occupy the upper right corner of the diagram, enormous in radius and cool in surface temperature, held in equilibrium by the slow upward transport of energy through convective envelopes that span much of their vast interiors. The radius that results from this expansion is something that resists easy comparison. A star that began its main sequence life with a radius perhaps 10 or 15 times the Sun's has, by the time it reaches the red supergiant phase, swollen to hundreds of times that original size. The most extreme red supergiants reach radii of 700, 1,000, 1,500 times the Sun's radius. The Sun's radius itself, roughly 696,000 kilometers, is already a distance that light crosses in a little over 2 seconds. 700 of those radii, placed end to end, would reach nearly to the orbit of Jupiter. The surface of such a star, if placed where the Sun is, would engulf everything in the inner solar system without pause, swallowing Mercury and Venus and Earth and Mars, and the asteroid belt, and its outer edge would be glowing somewhere in the middle reaches of the outer solar system, well past the orbit of the fifth planet. That picture takes time to settle. It is not the same as stating a large number. It is more useful to stay with it a while, to consider that the space currently occupied by the Earth's orbit, the full 365-day path that separates winter from summer, perihelion from aphelion, would lie entirely inside such a star. There would be no orbit. There would be only interior. The gas at the radius corresponding to the Earth's current position would be stellar atmosphere, tenuous, hot in its way, but not free space. And the star's photosphere, where light finally escapes outward, would be glowing far above, at a distance measured in hundreds of millions of kilometers from a center that the Earth currently occupies. The molecular cloud that began all of this has by now been transformed almost beyond recognition. The cold, dark cloud that drifted for millions of years, whose interior was only a few degrees above absolute zero, has been replaced by something that radiates at a luminosity tens or hundreds of thousands of times greater than the Sun. The gas that was locked in quiet molecular bonds, carbon monoxide, water ice, frozen nitrogen, has been heated, ionized, fused, and cycled through reactions that produce helium and release photons. The cloud's patience and gravity and cold have been converted over millions of years into light and heat and the deep red glow of a stellar surface, 4,000 degrees hot. The process that carried it from cloud to red supergiant is not a series of abrupt events, but a continuous chain, each link generated by the conditions of the previous one. Gravity begins the collapse, Collapse heats the core. Heat ignites fusion. Fusion produces energy that holds the star up. The star's hold on its core, hydrogen loosens over millions of years. The hydrogen runs out. The core contracts. The contraction expands the envelope. The envelope cools. The cool surface finds its equilibrium against the Hayashi limit. The star settles into its red supergiant phase, vast, cool at the surface, brilliant in total, and held at the edge of what is thermally possible for a body in hydrostatic balance. Every step in that chain follows from the one before. None of it required direction or purpose. Gravity does not intend to make stars. Fusion does not intend to produce light. The expansion of an envelope across tens of thousands of years is not heading anywhere. It is simply the consequence, step by step, of the physical conditions of each preceding moment. And the result of all those undirected steps is something that, if placed at the center of the solar system, would swallow the planet from which these words are spoken. Inside the red supergiant, the physics is still running. The helium that accumulated in the core during the hydrogen burning phase has now been compressed and heated to the point where it too has begun to fuse. Helium fusion produces carbon and oxygen, and it proceeds at a higher temperature and a faster rate than hydrogen fusion did. The core is contracting and heating in its center while helium burns in a shell, while hydrogen still burns in a shell above that, and while the vast convective envelope above all of it churns slowly, carrying energy upward to the surface. The star's interior is layered and complex, a nested structure of reactions at different temperatures and depths, each one releasing energy that flows upward through the structure and eventually escapes from the photosphere as the deep red light that makes these stars visible. That photosphere is not a fixed boundary. It is the layer from which light can escape without being immediately reabsorbed, where the gas is thinned enough and the geometry has opened enough for photons to travel freely outward. For a red supergiant, this layer sits far from the center, at the outer edge of the enormous inflated envelope, in gas that is extraordinarily tenuous by any terrestrial standard. The pressure at the photosphere of a red supergiant is far lower than what would be considered a laboratory vacuum on Earth. The material is present, but barely thin enough that light moves through it and away. Above the photosphere, the star does not end cleanly. The gas continues outward, thinning with distance, blending into a vast circumstellar envelope. Material ejected over long timescales accumulates in this space, gas and dust thrown off by the star's own wind and pulsation, drifting outward at tens of kilometers per second, cooling as it goes. The circumstellar envelope of a red supergiant can extend for hundreds or even thousands of solar radii beyond the photosphere, and it is not empty. It carries material. It reflects and scatters the star's light. It absorbs and re-emits at wavelengths that carry the signature of dust, silicate grains, carbon particles, molecules frozen out in the cold regions furthest from the star. This extended material means that even the definition of the star's size becomes complicated at its edges. A measurement taken in visible light finds the photosphere. A measurement taken in the infrared, sensitive to the warm dust of the circumstellar envelope, may find an apparent boundary many hundreds of solar radii further out. Neither measurement is wrong. They are describing different layers of the same enormous object, the same star seen at different depths. The number that goes on a diagram or in a table depends on which layer is being measured, and the choice is not always obvious. This softness at the edges is a consequence of how these stars evolved. A star that has grown through the gradual expansion of an outer envelope, driven by the energy of a contracting core and a burning shell, does not produce a surface with the clarity of a glass sphere. It produces an object whose density falls off gradually with radius, whose gas thins from interior density through photospheric transparency to circumstellar tenuity over a continuous gradient. The star's boundary is wherever the observer decides to call it, based on the physics of the measurement. In the cold dark of the molecular cloud that preceded all of this, nothing foretold this gradual ambiguity at the edges of enormous things. The cloud was defined by its own density gradient, not sharply bounded either, but fading into the interstellar medium at its edges in a similarly gradual way. What the cloud was at its center, dense and dark and cold, it became less of at its edges. What the red supergiant is at its core, dense, hot, layered with fusion, it becomes less of at its surface, and less again in the circumstellar material surrounding it. Both are structures without clean definitions at their boundaries, grown from physics that produces gradients rather than edges. The giant molecular cloud that drifted in the darkness, barely warmer than nothing, will not drift that way again. The part of it that formed this star has been consumed, drawn in, across hundreds of thousands of years, fused and transformed and radiated away as light. What was cold molecular gas is now helium in a stellar core, or photons crossing interstellar space, or warm dust in a circumstellar shell drifting slowly outward. The atoms did not disappear. They changed their arrangement, their state, their temperature, their relationship to one another. They passed from the cold order of a molecular cloud into the hot disorder of a stellar interior and the slow expansion of a stellar wind. That passage from cold cloud to massive star to red supergiant hovering at the edge of what the Hayashi limit permits covers millions of years. No human civilization is old enough to have watched any part of it in real time. The stars visible as red supergiants tonight began their journeys in molecular clouds that collapsed before any human being existed, in some cases before the genus that includes humanity had diverged from its ancestors. They have been burning their way through their nuclear fuel in the time that land animals were evolving, flight, in the time that the continents were arranging themselves into their current shapes, in a duration that contains the entirety of recorded history as the thinnest imaginable sliver. And yet they are here, now, visible in winter skies, glowing with the light of their contracted helium cores and burning shells, their surfaces cooled to the deep red that the Hayashi limit sets as a floor. They arrived at this phase by the slowest possible route, gravity's patience, nuclear fuel's gradual exhaustion, the tens of thousands of years of envelope expansion, and they will not remain here forever. But tonight they hang in the darkness, their photospheres diffuse and enormous, their circumstellar envelopes drifting outward, invisible in infrared, their interiors layered with the products of millions of years of fusion. The molecular cloud that began all of this is gone now, scattered and transformed, its cold molecular gas remade. What remains is a star that the cloud could not have predicted and did not intend, an object shaped entirely by the undirected operation of gravity and pressure and nuclear physics across a gulf of time that the human mind can name but never quite hold steady. The Hayashi limit stands at the edge of the Hertzsprung-Russell diagram, like something that was always there, waiting for the star to arrive at it, a boundary set not by any particular star, but by the deep structure of how matter and energy behave in a body held up by its own pressure against its own gravity. The red supergiant reaches that boundary and rests there, as cool as it can stably be, as large as its envelope can stably grow, hovering at the edge of the thermally possible in a quiet equilibrium that will last by stellar standards, not very long, but that tonight reads as stillness and as an ancient, unhurried calm. At a certain luminosity, the light inside a star becomes as strong as the gravity holding it together. Not stronger, not yet, just equal. The photons pressing outward and the mass pressing inward arrive at a perfect trembling balance, and the star hangs in that equilibrium the way a scale hangs when both sides carry identical weight. This is the threshold that determines how large a star is permitted to become. Not the temperature of its core, not the age of its fuel, not the depth of the cloud from which it formed, but the specific luminosity at which its own light becomes a force to reckon with, a pressure equal to the one that made it. The threshold has a name. It is called the Eddington luminosity, after the astronomer who first calculated it, and it scales with the mass of the star in a clean, simple way. For every solar mass of material, the maximum sustainable luminosity rises by a fixed ratio, roughly 32,000 times the sun's output per solar mass of material, though the star's actual structure adjusts this in practice. What matters for now is the picture, a star radiating so intensely that its own photons begin to behave like a wind, pushing the outer layers upward with a steady cumulative force. Below the threshold, the star is stable. Above it, the surface begins to lift. The balance point arrives near 150 solar masses. Stars more massive than this do not simply grow larger, they become structurally fragile, prone to shedding material faster than they can hold it, burning and shedding in overlapping cycles that prevent any further accumulation. The Eddington luminosity is not a wall. It is more like a tide line on a shore, matter piling up against it, cresting it, spilling back. The universe does produce stars near this limit, but they do not endure, and they do not grow past it for long. Below that limit, in the domain of the red supergiants and the largest stellar bodies, the structure is different. The light is not hot enough, not blue enough, not fierce enough to push the outer envelope away by radiation pressure alone. The danger is subtler, the forces more entangled, and the physics more difficult to hold in a single image. But the forces are no less real for that. A red supergiant persists in a slow negotiation between the weight of its own bulk and the heat rising from its core. And that negotiation is never fully resolved, never simply settled, for as long as the star lives. Deep inside a massive star, the pressure supporting the whole structure against gravitational collapse comes from two sources at once. One is thermal pressure, the ordinary push of hot gas against the walls of its container, the same force that inflates a balloon or holds up the atmosphere. The other is radiation pressure, the cumulative push of the photon field itself, the vast internal light of the star pressing outward against the gas from inside. In a star like the Sun, radiation pressure contributes very little to the total. The Sun is mostly held up by gas, but above roughly 40 solar masses, the balance begins to shift. In the most luminous stellar interiors, more than half the total outward pressure comes not from heat, not from the motion of atoms, but from the light the star makes in the process of fusing hydrogen. The interior is held up less by gas than by its own glow. This matters enormously for how stable such a star can be. A structure held up by gas can absorb small shocks. Gas pressure responds to temperature changes in a stabilizing way. If the core runs slightly hotter, the gas expands, the density drops, and the reaction cools back down. The system has a restoring force. But radiation pressure responds to luminosity, and luminosity depends on nuclear reaction rates, and nuclear reaction rates depend on temperature in a steep nonlinear way. A slight brightening increases radiation pressure, which expands the envelope, which changes the opacity, which changes how much light escapes, which changes the pressure again. The feedback loop runs in several directions at once, and the star's ability to damp out small oscillations becomes weaker the more of its support comes from light rather than from gas. Very massive stars live in a kind of structural delicacy, permanently near the edge of a condition they cannot quite cross, adjusting continuously to stay in balance. The red supergiant does not face this problem in quite the same way. Its luminosity is high but not so extreme, its radiation pressure not so dominant. What it faces instead is the consequence of its own size, specifically the enormous, slow-churning envelope of gas that surrounds its core, extending outward for hundreds of solar radii in all directions. This envelope is not passive, it is convective, which means it carries heat not by radiation, but by the motion of gas itself, great slow columns of material rising from the hotter interior, cooling as they rise, and sinking back down again to be reheated. The sun does this on a small scale, in a thin layer near its surface, producing the granular texture visible in high-resolution images of the photosphere. Millions of small cells, each one a column of rising and falling gas, each one about the size of Texas, living for a matter of minutes before sinking and being replaced. In a red supergiant, the convection is different in every way. The envelope is vastly deeper, the temperature gradient much shallower, and the result, according to the best available numerical models, is not millions of small cells, but a small number of enormous ones. Perhaps a handful, perhaps fewer, each spanning tens of degrees of arc across the star's surface. Each one would be large enough that, placed beside the sun, it would dwarf it completely. A single column of rising gas covering more of the star's face than any continent covers the Earth's. These are not the tidy granules of a solar photosphere. They are slow, enormous, churning masses of plasma rising over months or years, cooling and darkening as they spread, and sinking back along pathways that shift and reform over timescales no human observer will ever watch in full. The evidence for this picture comes from optical interferometry, the same technique that resolves the disk of a red supergiant as anything other than a point of light. When the resolved images are examined carefully, they show that the stellar disk is not uniformly bright. One region glows more intensely, another sits darker, cooler. The brightness is patchy, uneven, asymmetric in ways that change over the months and years that observations accumulate. Some of this asymmetry is attributed to these great convection cells, each one a hot bright upwelling or a cool dark sinking, each one large enough to be seen from hundreds of light years away in the resolved image of a disk only a few milliarc seconds across. The surface of a red supergiant is not a smooth glowing sphere. It is alive with slow, enormous motion, like the surface of a pot of very thick liquid heated from below, stirred by columns wider than most stars. This convective churning is one of the driving forces behind the pulsation of red supergiants. A red supergiant breathes, in a sense, its outer layers swelling and contracting on timescales ranging from hundreds of days to several thousand. The swelling is not regular. It does not repeat like a clock, does not tick with the clean period of a variable star driven by a single organized process. Instead, it is a slow, layered, overlapping motion, several rhythms running at once, sometimes reinforcing, sometimes partially canceling, so that the brightness measured on any given night is the sum of a complex interference of cycles rather than the simple rising and falling of one. The variation is real and large enough to be measured from Earth. The period is real in a statistical sense, but no observer watching the star night after night will ever see it repeat exactly, because the system that produces the variation is too complex for that kind of precision. The comparison that clarifies this is with another class of variable star, the Cephid. A Cephid variable pulsates with extraordinary regularity, its brightness rising and falling on a period that stays constant to within a small fraction of a percent over years and decades. The mechanism is clean and well understood. A layer of partially ionized helium within the stellar envelope acts as a valve, becoming more opaque as it compresses and more transparent as it expands, driving the pulsation in the same direction each cycle, maintaining the rhythm like an engine regulated by a single governor. The result is a clock so reliable that astronomers use Cephinus to measure distances across the galaxy. A red supergiant has no such mechanism. Its pulsation is not driven by an opacity valve working in a regulated cycle. It is driven by convection, by the slow, irregular churning of that enormous envelope, by the rise and fall of convective cells, whose timing is not fixed, whose influence overlaps and shifts, and the result is a variation that is semi-regular at best, irregular at worst, a slow breathing without a fixed tempo. Hundreds of days, then a different number of hundreds, a longer swell of 2,000 days, then a shorter one, then a slightly different one, never quite repeating. The pulsation matters for more than its own sake, because it is one of the things that drives material off the star's surface. A red supergiant is not a closed system. It loses mass continuously, not in the catastrophic flares of its hottest counterparts, not in the fierce radiation-driven winds of very luminous blue stars, but in a slow, persistent, quiet outflow that carries stellar material into the surrounding space gram by gram, second by second, across time scales measured in hundreds of thousands of years. The wind is gentle by stellar standards. It leaves the photosphere at speeds of 10 to 50 kilometers per second, fast enough to cross the continental United States in a minute or two, but slow compared to the winds of hot massive stars, which move at hundreds or thousands of kilometers per second. What drives the wind is an interplay between the stellar luminosity and the grains of dust that form in the cool outer layers. Close to the stellar surface, the temperature is too high for dust to condense, but a few stellar radii where the temperatures have dropped to a few hundred to 1,000 Kelvin, the conditions allow solid particles to form, grains of silicate and carbon and aluminum oxide, mineral compounds that are, in their chemical families, related to the rocks beneath the ground of every terrestrial planet. These grains, once they form, are highly effective absorbers of the stellar radiation streaming outward from below. Photons push on them. Each individual photon carries momentum, and when it is absorbed by a grain, that momentum is transferred. One photon does nothing. Billions of photons per second, streaming outward through a cloud of freshly condensed grains, accelerates them slowly, and as the grains move outward, they drag the surrounding gas with them through collisions, and the gas moves too, and the whole outflow lifts gently away from the star. The result, over a long time, is significant. The mass loss rate of a typical red supergiant lies somewhere between a 10 millionth and a 10,000th of a solar mass per year. At the low end, this is a modest flow. At the high end, during periods of elevated mass loss driven by heightened pulsation or particularly intense convective activity, the star sheds mass fast enough to build a new sun in 10,000 years. Over the full lifetime of the red supergiant phase, which may span 100,000 years or more, the total mass lost to this slow wind can amount to several times the mass of the sun. A star that entered the red supergiant phase with 15 solar masses might arrive at the end of it with considerably less, its outer envelope thinned and dispersed, its circumstellar environment filled with expanding shells of gas and dust drifting outward at the same gentle speeds at which they left. Those shells are not invisible. They glow, not in the wavelengths of visible light, not with the warm orange-red of the stellar photosphere, but in infrared. The dust absorbs the optical and ultraviolet light streaming from the star below and re-radiates it at longer wavelengths, the kind that human eyes cannot detect, but that infrared telescopes map in detail. Around many red supergiants and hypergiants, these shells have been resolved into complex structures, multiple layers, asymmetric lobes, dense knots, and filaments of material ejected in different episodes at different rates, the accumulated record of centuries and millennia of slow shedding written in glowing dust. The star VY Canis Majoris, one of the most studied examples, is surrounded by a circumstellar nebula that is among the most complex in the sky, filled with arcs and clumps and sheets of material thrown off across many separate mass loss events, each one different in mass and direction, a record of the star's turbulent recent history preserved in the geometry of the surrounding gas. This complexity is part of why measuring the size of a red supergiant is harder than it sounds. The star does not end cleanly. Its photosphere, the layer from which most of the visible light escapes, is diffuse, its boundary a gradual transition rather than a sharp edge, extending across a range of depths as the gas becomes less and less opaque to the light trying to pass through it. Beyond the photosphere, the chromosphere and the inner circumstellar environment blend with the star's outer atmosphere in ways that different observing wavelengths sample differently. An observation at one infrared wavelength will measure a stellar radius consistent with one value. An observation at a slightly different wavelength, sensitive to different layers of the extended atmosphere, will give a different value. The dust shell scattered around the star contributes emission at some wavelengths and absorption at others, further complicating the picture. The number that ends up in the literature as the stellar radius is always a measurement at a specific wavelength under specific assumptions, a best available estimate, not a definitive boundary. This ambiguity is not a failure of measurement, it is a true feature of the object. The star is genuinely uncertain at its edges. The largest stellar bodies in the universe are also the least precisely defined, not because the instruments are inadequate, but because the stars themselves do not have sharp edges to define. They thin out gradually into a surrounding region of ejected material that is itself still stellar in its origin and composition, a realm where the boundary between star and space is more a matter of convention than physics. What is called the stellar radius is, in practice, the radius of the layer that contributes most of the observed light at the wavelength of observation, a useful number, a meaningful number, but not the final word on where the star stops. The pulsation adds a further layer of complication. Because the outer envelope is moving, swelling, and contracting on timescales of hundreds to thousands of days, the photosphere is not even at a fixed depth. As the star swells, the photosphere moves outward, increasing the measured radius. As it contracts, the photosphere moves inward, decreasing it. The measured radius of a red supergiant is therefore also a function of when it is measured, varying by tens or even hundreds of solar radii between the expanded and contracted phases of the pulsation cycle. The published values are averaged across multiple observations or tied to a specific phase, but the underlying variation is real and large by any human standard. Across a long stretch of time, 100,000 years of gentle, persistent outflow, the effect on the star accumulates. What began as a massive object surrounded by nothing but its own light eventually becomes the center of an expanding cocoon, a warm, dark region of slowly moving dust and gas that records the star's recent history in its geometry and chemistry. The cocoon dims the stellar light at some wavelengths and redirects it at others. It creates a local environment around the star that is partly of the star's own making, an atmospheric region that is neither star nor space, where conditions differ from both. This is the circumstellar envelope in its fullest sense, not just a thin shell, but a layered, structured, chemically complex region built up over time by the continuous outflow. In this envelope, chemistry happens that does not happen anywhere else. The temperature is cool enough for molecules to form water vapor, carbon monoxide, silicon monoxide, and many others, and these molecular species emit radio and microwave radiation that can be detected from Earth. Molecular maser emission, in particular, has been mapped around several red supergiants, spots of intense coherent radio emission arising from populations of molecules stimulated to radiate in phase. The positions and motions of these masers allow astronomers to trace the velocity structure of the circumstellar envelope and to measure the expansion of the outflow with precision, using the molecules the star shed as markers for the shape and speed of the wind. The star writes its own history in the gas it casts off, and the gas carries that history outward at tens of kilometers per second, slowly expanding, slowly cooling, slowly thinning into the surrounding interstellar medium. The forces operating inside a red supergiant, gravity, thermal pressure, radiation pressure, convective motion, pulsation, and mass loss do not operate in sequence or in isolation. They are entangled. The pulsation modulates the mass loss rate. The mass loss affects the stellar luminosity by removing envelope mass and changing the opacity structure. The opacity affects how radiation moves through the interior, which affects the convective pattern, which drives the pulsation. The whole system turns in a slow, coupled cycle, each force shaping the others, none of them cleanly separable into cause and effect. This is part of what makes modeling these stars difficult, and part of what makes measuring them ambiguous. But it is also part of what makes them what they are, not simple objects defined by a few numbers, but slow, complex systems operating at the edge of their own stability, shaped by the interplay of forces across the full extent of their enormous bodies. An observer stationed far from one of these stars, far enough to see the whole disk of the circumstellar envelope against the background sky, would see very little invisible light. The star itself would be a dim red point, its surface hidden behind layers of its own dust. In the infrared, the picture would be different. The envelope would glow in broad, warm lobes around the stellar center, its structure irregular and asymmetric, brighter in some directions than others, marked by knots and filaments and thin expanding shells set one inside another like the rings of a tree. The expansion would be invisible to any quick glance, the outermost shells moving outward at 50 kilometers per second, which at stellar distances changes the observed geometry only over decades or centuries. But over the long arc of time, the expansion would continue without pause, the dust moving outward through interstellar space long after the star that made it had changed into something else entirely. This slow, persistent drift of dust into the surrounding galaxy is one of the ways red supergiants enrich the interstellar medium. The silicate and carbon grains they produce, condensed in the cool outer regions of their circumstellar envelopes, are chemically complex and physically durable. They drift outward, cool further, and eventually disperse into the general medium of gas and dust, from which future generations of stars will form. In this sense, the mass a red supergiant sheds through its slow wind is not lost. It is returned, chemically enriched by the star's nuclear history, processed and repackaged in new mineral forms, and sent back into the pool from which new stellar systems eventually emerge. The dust that gathers in a newly forming protostellar disk, eventually settling into planetesimals and rocky planets, carries within it the mineral output of all the red supergiants that came before. Generations of slow winds and dusty outflows, each contributing a quiet share to the chemistry of what follows. The internal life of a red supergiant, then, is not the serene and featureless stability that its steady glow might suggest from a distance. It is a slow, continuous negotiation between competing forces, played out across timescales that make any individual event difficult to observe in full. The convection cells rise and fall over months and years. The pulsation accumulates over hundreds and thousands of days. The wind carries mass outward over tens and hundreds of thousands of years. At each timescale, the star is doing something, adjusting, shedding, fluctuating, redistributing, and none of these processes fully settles before it is overtaken by the next cycle. The star does not reach equilibrium. It hovers near it, always slightly displaced, always in the process of returning to a balance it never quite achieves. There is something in this that is easier to feel than to describe. A star of 700 solar radii, glowing in the deep orange red of a surface near 3500 Kelvin, surrounded by a warm cocoon of its own dust, pulsating slowly on overlapping cycles, losing a thin stream of material to space with every passing year. This is not a simple object. It is not a ball of fire in the way that simple pictures of stars tend to suggest. It is a layered, stratified, slowly evolving system, its boundary undefined, its behavior never exactly repeated, its history written in the dust shells that surround it. And the forces that shape it are the same forces that govern all of stellar physics: gravity, pressure, opacity, convection, but acting here at scales and in combinations that produce behavior different from anything that can be observed in a smaller star. The Eddington luminosity sets the outer boundary. Below it, stars can exist. Near it, they become unstable. Far below it, in the domain of the red supergiants, the instability is of a different character, not the fierce radiative instability of the most luminous blue stars, but the slow structural fragility of enormous envelopes that cannot quite settle, that pulse and shed and drift in a continuous slow motion that lasts for the full duration of the red supergiant phase. The star is not falling apart, but it is always, in a small way, letting go. The dust that leaves the photosphere at 10 kilometers per second will still be moving when the star that made it is gone. It will have passed through the stellar system's surroundings, dispersed into the general interstellar medium, its individual grains drifting separately on slightly different paths, cooling toward the temperature of the background of space. The light that warmed it, the infrared glow of the circumstellar envelope, will have faded long since. The star's core will have done what stars like this eventually do, and the dust will simply continue, moving outward, unchanged in its chemistry, carrying in its mineral composition the faint record of a star that once held the mass of many suns, and slowly, patiently gave much of it back. At a certain point outward from a red supergiant, beyond the bright molecular shell, beyond the layers where masers form, beyond the dense inner envelope, the ejected material has thinned enough that it is indistinguishable from the general surrounding gas. Not a sharp transition, not a clean boundary, just a gradual fading of enriched material into the older, less processed medium that fills the space between stars. The star's influence does not end at a line, it ends at a distance, and that distance is different at different wavelengths, different for different chemical tracers, different depending on how long the star has been losing mass, and at what rate and in which direction. The edge of a red supergiant's influence, like the edge of its photosphere, dissolves rather than stops, thinning outward into the surrounding dark at the same gentle pace at which the wind that carried it first left the surface, tens of kilometers per second, a pace that has been constant across 100,000 years of slow, unhurried departure. In the lower right corner of Orion, a blue-white point of light holds steady against the winter dark. It does not flicker the way a candle does. It burns with a cold, even clarity, the kind of brightness that seems almost deliberate, almost architectural, as though something very far away has been arranged to be seen. That star is Rigel, and in the upper left of the same constellation, close enough that a single glance can hold both at once, another star glows at a different color entirely. A deep, soft amber, almost orange, the color of embers seen from across a room. That star is Betelgeuse. Between them stretches the belt of Orion, 3 stars in a row, and the distance in the sky between one corner and the other is small enough that a child's hand held at arm's length could cover it. The 2 stars share a constellation. They share a hemisphere of winter sky. In almost every other way, they are as unlike each other as 2 stars could be. These are both supergiants. The word covers a range so wide that it barely suggests similarity. A supergiant is simply a massive star that has moved past the long central phase of its life, the phase where hydrogen burning holds everything in a steady balance, and has entered the larger, more complicated territory that follows. What a star does in that territory depends on a great many things: its mass, the particulars of how its outer layers respond as its core contracts, the way energy moves through it, and the result can look almost entirely different from one star to the next. Rigel and Betelgeuse are both the product of that passage. Both are among the most luminous stars in the sky, as seen from Earth. Both belong to the same thin tier of stellar rarity, the uppermost strip of the diagram that plots a star's brightness against its color, where only the most extreme objects reside. They arrived at that tier by entirely different means, and they do not resemble each other at all. Betelgeuse's surface, at around 3,500 Kelvin, is cooler than any flame a person would see in daily life. An ordinary candle burns hotter at its wick. The sun's surface, by comparison, runs at roughly 5,800 Kelvin, and even that is considered moderate by stellar standards. Betelgeuse sits far below both, its outer layers so vast and diffuse and cool that the light emerging from them shifts well toward the red end of the visible spectrum, the part where wavelengths lengthen and energy per photon drops. What comes from its photosphere is amber-orange light, low in blue and violet, rich in red and infrared, the color palette of something enormous and slowly glowing rather than something hot and fierce. That coolness is not weakness. It is the consequence of an envelope so expanded, so many hundreds of millions of kilometers thick, that the energy generated deep in the core is almost unrecognizably diluted by the time it reaches the surface. The same total energy spread across a surface area that would dwarf the inner solar system produces a cooler, redder glow, vast and dim by temperature, still blindingly luminous by any human standard. Rigel, at the other corner of the constellation, runs its surface at around 12,100 Kelvin. that is more than 3 times hotter than Betelgeuse, and the difference in temperature shows itself immediately in the color of the light. Above roughly 7,000 Kelvin, stars shift from white to blue-white, the short wavelength end of the visible spectrum carrying more of the total energy, and at 12,000 Kelvin, the blue component is strong and clean and unmistakable. Rigel's radius is roughly 79 solar radii. By any ordinary measure, that is a large star, wider than many stars that will spend their entire lives on the main sequence, larger than anything in the solar neighborhood that a person could call typical. Against Betelgeuse, which spans somewhere between 700 and 900 solar radii, depending on which part of its irregular, pulsating, dust-shrouded surface one is measuring. Rigel is compact. It is a hot, dense point of intense emission. Betelgeuse is a vast, cool, slowly churning sphere whose outer layers have drifted outward to a distance that would swallow Mercury, Venus, Earth, and Mars without any of those planets registering as more than a slight disturbance in the gas. The surface area of a star scales with the square of its radius. The total energy a star radiates, its luminosity, scales with both surface area and the fourth power of surface temperature. These two scalings pull in opposite directions when comparing Rigel and Betelgeuse. Rigel's much smaller radius gives it far less surface area. Its much higher temperature gives each square unit of that surface a dramatically greater power output. Betelgeuse's much larger radius gives it an immense surface area. Its much lower temperature drains the power from each unit of that surface. Working through the numbers, both stars end up in a similar luminosity range, among the most luminous stars visible to the naked eye from Earth, each outshining the Sun by tens of thousands of times, though by different routes. Temperature matters as much as size. A cooler star must grow very large to keep pace. A hotter star can remain compact and still pour light into space at a rate that rivals its expanded neighbors. On the diagram that plots stellar brightness against color, with luminosity on one axis and temperature on the other, these two stars occupy opposite corners of the same high tier. Betelgeuse sits to the upper right, faint in color, meaning red and orange, high in luminosity. Rigel sits to the upper left, brilliant in color, meaning blue-white, equally high in luminosity. Between them, across the diagram, stretches a wide band of empty space where ordinary stars do not spend long. To pass through that middle ground takes time, the slow geological-paced reshaping of a stellar envelope that takes tens of thousands of years to play out, and most stars passing through it do so without lingering. The two corners of the diagram are the places where stars can, for a time, hold still. One corner is hot and compact and blazing, the other is cool and vast and slowly burning through what remains. Betelgeuse reached its current state after its core exhausted its hydrogen supply. What had been a hot, compact, blue-white star, probably similar to Rigel in some respects, though more massive, began a transformation as its core, no longer generating enough energy to support the outer layers, contracted inward. The inward contraction of the core released gravitational energy, which pushed the outer envelope in the opposite direction. Over tens of thousands of years, the outer layers swelled, the surface area grew. The surface temperature dropped, as the same energy was now distributed across an ever larger sphere. The star moved, in the language of that diagram, from the upper left toward the upper right, cooling and expanding as it went. It crossed the whole width of the temperature range, from blue-white through yellow through orange and into red, arriving at last at the cool, vast, convectively turbulent configuration it holds today. That crossing was not violent. Nothing about it would have been visible to any observer watching on human timescales. It was a drift, a slow motion expansion whose pace would have made the growth of mountains seem hurried. Rigel may have undergone some version of this already, or may yet. The evolutionary paths of massive stars in this mass range are complex, and some stars perform what are called blue loops, expansions to the red end of the diagram, followed by a contraction back toward hotter configurations, then possibly another expansion. Rigel may be a star that expanded, contracted, and now sits in a hot compact phase that will not last indefinitely. No one can say with certainty whether it has already visited the red region of the diagram or will do so later. What is clear is that it currently occupies the hot end, and that the two stars, sharing a sky, sharing a constellation, visible side by side on any winter night, represent two very different chapters of what are, at the deepest level, two variations on the same story. The spectral classes that contain these stars tell their temperatures at a glance to anyone who has learned the sequence. Red supergiants like Betelgeuse fall in spectral classes M and K, the cooler end of the range, where molecular absorption features from titanium oxide and vanadium oxide appear in the spectrum, alongside the usual lines of common elements. These molecular features only survive in atmospheres cool enough that the molecules are not broken apart by radiation, and their presence in a stellar spectrum marks the star immediately as something below about 4,500 Kelvin. Blue supergiants like Rigel fall in spectral classes B and O, where the spectrum is dominated instead by lines of ionized hydrogen, ionized helium, and other species that require a hot, energetic photon field to maintain their ionization states. The spectrum of a star is not just a list of its elements, it is a thermometer readable across any distance from which the light can be gathered. The light from Rigel has been traveling toward Earth for around 860 years. The light now arriving left that star roughly at the time of the 13th century, when the atmosphere around it was already producing the same blue-white spectrum it produces today. The light from Betelgeuse takes around 700 years to cross the same gulf, having left the star sometime in the 14th century. When the two lights arrive together in the same winter sky, one from 860 years ago and one from 700 years ago, they are not quite contemporaries even in that sense. The sky holds a kind of temporal layering that never resolves into a single present moment. Each point of light is a different depth of the past, and the pattern of stars a person sees on any given night is a mosaic of separate historical moments laid over each other in the same visual plane. Rigel's light, despite originating from a physically smaller star, carries more power per unit area at the surface than Betelgeuse's does. 12,000 Kelvin versus 3,500 Kelvin is not merely a difference in color, it is an enormous difference in the energy density of the photon field at the stellar surface, and in the spectrum of that emission. Rigel radiates heavily in the ultraviolet, wavelengths shorter than the eye can see, carrying more energy per photon than any visible light. Much of what Rigel emits is, strictly speaking, invisible. The blue-white light a person sees in the winter sky represents only part of the output, the fraction that falls within the narrow window of wavelengths the human eye responds to. Betelgeuse, by contrast, peaks in the red and near-infrared, and a significant portion of its emission falls in the infrared, also invisible, but at the long wavelength end rather than the short. Both stars are partly hidden from the naked eye, though for opposite reasons, their full emission extending into portions of the spectrum that human vision never evolved to reach. It is one of the stranger qualities of the Hertzsprung-Russell diagram that it organizes stars by the exact properties least accessible to unaided observation. Temperature shows up as color, and color is perceivable, but only across the narrow visual range. Luminosity requires knowing the distance which is not visible. A star's position on the diagram must be calculated from what is measured: apparent brightness, distance, spectral features, and only then does the underlying structure become clear. Rigel and Betelgeuse appear in the same patch of sky at comparable apparent brightnesses. Rigel somewhat brighter to the eye on most nights, Betelgeuse somewhat variable. Their true luminosities corrected for distance are both extreme, but the diagram shows them arriving at that extremity from two different directions, two different temperatures, two different physical regimes. Temperature and size together determine luminosity, and the diagram is simply the plane in which those two contributors are laid out, so that the variety of stellar configurations can be seen all at once. There is a quality of stillness to Rigel that does not characterize Betelgeuse. Rigel's light is relatively steady, its surface conditions more uniform, its brightness monitored across centuries, showing only small variations without the episodic surges and dimmings that make Betelgeuse a subject of constant observation. This relative steadiness comes in part from the structure of a hot, compact star, where convection in the outer layers operates differently, producing many small cells rather than the handful of enormous churning columns that cover significant fractions of a red supergiant's disk. The surface of Rigel, if one could somehow observe it at high resolution, would show a more even texture, the granulation pattern familiar from the Sun, scaled up for a larger and hotter star, but not dominated by any single enormous feature. Betelgeuse's surface, by contrast, is believed to show only a few of these giant convection cells at any one time, each one spanning tens of degrees, each one rising and falling slowly over months, reshaping the star's apparent brightness and contributing to its irregular variability. That variability, the slow overlapping pulses of a red supergiant, has no equivalent in Rigel. Red supergiants pulsate on timescales of hundreds to thousands of days, multiple rhythms interfering and reinforcing each other in a pattern that never quite repeats. This is not the clean clock-like behavior of a Cepheid variable, where a well-understood physical mechanism drives precise, reproducible cycles that observers have used for a century as a tool to measure cosmic distances. The pulsation of a red supergiant is something looser, more organic, driven by the vast churning of its convective envelope rather than by a clean resonance. Betelgeuse carries at least two distinguishable periods within it, one of roughly 400 days, one stretching to around 2,100 days, and the interplay between them means that its light rises and falls on a schedule that can be partially anticipated but never exactly predicted. Rigel has no such deep rhythm. Its surface does not heave on a seasonal clock. The mass loss rates of the two types also differ substantially. Red supergiants, driven by radiation pressure acting on dust grains that condense in their cool, slow-moving winds, shed material at rates that can strip away several solar masses over the last 100,000 years of a star's life. The wind leaving a red supergiant is not fast, 10 to 50 kilometers per second, slow by the standards of the fierce winds that pour from hot luminous stars, but it is dense and it carries real mass into the surrounding space, building over time into an extended circumstellar envelope that can be detected in the infrared. Rigel and its class of blue supergiants also drive winds, and theirs are faster, driven by radiation pressure acting on the gas directly rather than on dust. The wind velocities can reach several hundred kilometers per second. But the density of a blue supergiant wind is lower, and the total mass carried off over the same period is generally less than what a red supergiant sheds. It is another asymmetry between the two types, the cool, slow wind versus the hot, fast one, each carrying material outward, each slowly reducing the star's mass, but doing so in different ways and at different rates. The circumstellar environment around Betelgeuse shows the history of its mass loss written in the surrounding space. Material ejected over tens of thousands of years has formed a complex of shells and arcs and asymmetric structures detectable in the radio, the infrared, and the far ultraviolet. This material was once part of the star's outer atmosphere. Some of it was part of its photosphere. Dust that formed in the cooling ejecta has been drifting outward ever since, a slow halo of cast-off stellar matter that will persist long after the star itself is gone. Rigel's circumstellar environment is different in character. The faster, more diffuse wind leaves traces as well, but the structures are generally less prominent in the infrared, less laden with dust, more transparent to the eye of instruments looking for the quiet signatures of accumulated mass. In Orion, both stars are close enough in angle that their light falls within the same telescope field at low magnification, and the contrast between them is immediate. The blue-white of Rigel and the amber of Betelgeuse are both extreme cases of stellar color, each pulled toward the opposite end of the range that normal stellar physics permits. Between them, strung through the middle of the constellation, are the other stars of Orion, Bellatrix, blue and hot, Saiph, similar to Rigel in spectral type, the stars of the belt, all blue-white-hot supergiants in their own right, and the nebulosity of the sword, where the light of new stars illuminates the cloud from which they were born. Orion contains an entire cross-section of stellar life, from the youngest and hottest to the most evolved and expanded, and the two supergiants at its corners are simply the most visible examples of a range that the constellation holds in a single frame. The night sky seen from a dark field on a winter evening holds Orion as a fixed landmark, its pattern clear and reliable across all of human recorded history. Every observer who has found Betelgeuse with their eyes, even without knowing anything about what they were seeing, has received light that left the star sometime in the 13th or 14th century, photons that crossed 700 years of interstellar space to fall on the retina. Every observer who has found Rigel in the opposite corner has received light that is slightly older still, having traveled for nearly 9 centuries. The constellation is not a fixed spatial object. It is a pattern projected by a human mind onto stars at wildly varying distances, and the two supergiants at its corners are not particularly close to each other in three-dimensional space. They happen to lie in roughly the same direction from Earth, at not entirely different distances, in a configuration that gives the illusion of proximity. The shoulder and the foot of Orion, as people have called them across civilizations, are unrelated objects that merely share a line of sight. The feeling of seeing both at once is something that requires no knowledge of stellar physics to produce. The eye notices the difference in color without any instruction. The amber and the blue-white are simply there, alongside each other, one steady and clear and bright, the other slightly variable and slightly softer in its glow, and the contrast between them is one of the sky's quieter pleasures, available to any person who looks up on a cold night and lets the eye travel from one corner of the constellation to the other. What the knowledge adds is depth, not novelty. The colors were always different. The knowledge only explains why, and in explaining, makes the stars more present rather than more abstract, more specific rather than more remote. A star at 12,000 Kelvin emits so powerfully in the blue-violet range that its spectrum, if spread out by a prism or a diffraction grating, shows hydrogen absorption lines sharp and prominent in the blue region. A star at 3,500 Kelvin emits so little blue light that its spectrum, spread the same way, would show the absorption bands of molecules, titanium oxide, among others, only in the red and near infrared, the blue end thin and faint. Two spectra, two different chemical fingerprints of temperature, two different windows into the same underlying physics. Heat changes the ionization state of every element in the atmosphere, and the spectrum responds accordingly, and the color of the arriving light is the average of that response passed through the long corridor of space and time. On the Hertzsprung-Russell diagram, a line drawn between the positions of Rigel and Betelgeuse would cross the full width of the upper tier, passing through the territories where orange and yellow supergiants occasionally spend brief periods during their crossings. That line traces the evolutionary path that many massive stars take at some point in their lives. Whether a given star crosses from blue to red or red to blue, or oscillates between both, depends on its mass, its composition, and the details of how it sheds material and redistributes energy within itself. For some stars, the crossing happens quickly, and they spend most of their remaining life at one end or the other. For others, the crossing back and forth may happen more than once. The diagram holds all of these as static snapshots, each star caught at one moment in a longer journey, and what looks like a stable arrangement of types is on stellar timescales, a slow and ongoing traffic of enormous objects moving back and forth across a temperature range that spans a factor of nearly 10. The companion Betelgeuse is sometimes imagined to have a cooler, redder twin somewhere nearby, visible only at the right wavelengths, does not exist in any confirmed form. What surrounds it instead is its own past, the material it has shed, the dust that now drifts slowly outward in a complex asymmetric envelope. The star's nearest stellar neighbors, in any meaningful astrophysical sense, are light years away. In the density of space that human beings occupy, stars are isolated objects separated by enormous empty intervals, and any two stars that share a night sky do so only because of geometry. The line of sight from this small planet aligns them by chance. Rigel and Betelgeuse share a sky. They do not share a neighborhood. Both will end. The way they end will likely differ. Very massive stars, those above a threshold that current models place somewhere between about 8 and 40 solar masses, depending on how one counts, generally end in core collapse events. The exact sequence depends on how much mass has been lost, what the core composition becomes, whether the collapse proceeds cleanly or not. Rigel, if it has not yet lost enough mass to change the picture, may end in a very different kind of event than Betelgeuse, whose more advanced evolutionary state and extended, dust-laden circumstellar environment already suggest a star that has been shedding itself into space for a long time. Neither will go quietly in the stellar sense, but neither end is imminent on any human timescale, and the two stars will continue to occupy opposite corners of Orion for longer than any civilization is likely to exist to observe them. The expansion that carries a massive star from the hot side of the diagram to the cool side, from compact and blazing to vast and slow and amber, is among the most transformative things a star does. Nothing visible announces it. The star does not flare or flash. Over tens of thousands of years, the outer envelope extends, the surface area grows, the color shifts. An observer with an infinite patience could watch the blue-white of a young massive star slowly warm through white toward yellow, then orange, then the deep red-orange of a mature red supergiant, as the outer layers swelled to distances that would have seemed impossible when the star was young and tight and burning hard. What had been a compact, fierce, radiatively dominated ball of gas gradually becomes something else entirely, something cooler, more convective, more irregular, more diffuse at its outer edges, its boundaries less defined, its mass slowly leaving through a wind that moves at walking speed compared to what the star once drove outward from its surface. And Rigel, for now, holds its color, blue-white, steady, sharp spectrum, compact relative to the vast cool star in the other corner of the constellation. It holds the configuration of a hot supergiant, without having yet fully resolved what the next long phase of its existence will bring. Some models suggest it may already have expanded and contracted, already crossed the diagram once and returned. Others suggest the great expansion lies ahead. The uncertainty is genuine, and no one observing Rigel tonight can see anything in its steady blue-white light that would resolve the question. What is visible is what is visible, a bright, cool-colored point, cool in the human sense, that is, calm and clear, burning at 12,000 Kelvin, with a surface that is, in any ordinary sense, almost incomprehensibly hot, radiating its energy steadily into the winter night from a distance of 860 years. In the same sky, Betelgeuse glows amber. It has already made the crossing that Rigel may not yet have made. It has already swelled to the dimensions that make it one of the largest stellar objects within any reasonable distance of the Sun. Its surface heaves slowly with enormous convection cells. Its brightness oscillates on rhythms of hundreds and thousands of days. Its outer envelope carries the record of mass ejected across millennia, where Rigel is held in a kind of taut stability. Betelgeuse is a star in a looser, more dynamic state, slower in its wind, vast in its extent, and richer in the dust and molecules that only form in cool, slow-moving gas. Both states, the hot, compact, brilliant blue, the cool, vast, amber glowing red, are real expressions of what a massive star can become when it moves past the long central chapter of its life. Neither is more final than the other, and neither tells the full story of where such stars are headed. They are simply two configurations, two corners of the same high tier, two stars sharing a winter sky and belonging to entirely different worlds. The slow crossing from one corner to the other takes longer than any human story. It takes longer than any civilization. From the perspective of the night sky, as seen in any single lifetime, or any single century, or any recorded span of human observation, the stars appear fixed. Betelgeuse has always been amber. Rigel has always been blue-white. The diagram appears to be a static map. What it actually represents is a population caught in motion, each star a snapshot of a moment in a longer arc, and the variety of types visible in any sky survey is the variety of stages that massive stars pass through at different rates on the same general path. The snapshot quality of it, the way the diagram looks fixed, is simply a function of human timescale. Given enough time, the upper tier of the diagram would show its stars flowing slowly from one end to the other, blue to red, and sometimes back, the whole population in a slow migration that no one lifetime can witness. On a clear winter night, the belt of Orion rises above the southeastern horizon in the hours after dark. The three stars of the belt emerge first at that latitude, then Rigel in the lower right, then the shoulder of Betelgeuse above and to the left. The sky darkens further, and the whole constellation becomes visible, and the contrast of its two anchor stars is simply there. No explanation needed to perceive it. No knowledge needed to sense that these are different kinds of fire burning at different temperatures across the same cold dark. The light takes roughly 7 to 9 centuries to arrive from either star, and the pattern it traces has been overhead for long enough that every human tradition that observed the winter sky has named it in some form. The two lights, amber and blue-white, have been available to any pair of eyes willing to stand in the dark and look up, for as long as there have been eyes. They will be available long after the eyes watching tonight are still. The constellation will persist, slowly shifting over the scale of tens of thousands of years as stellar proper motions carry each star along its individual path across the galaxy, gradually dissolving the pattern and building new ones. But for now, the two supergiants hold their places at opposite corners of the night, each burning in its own way, each telling a different part of the same long story, while the dark between them remains exactly as it always has been, quiet and cold and very old and still. In the winter of 2019, Betelgeuse grew dim, not dark, not gone, but noticeably, measurably, undeniably quieter than it had ever been in recorded memory. The orange star at Orion's shoulder fading over the course of weeks until it had lost roughly a third of its usual light. Astronomers who had watched it for years noticed first, then amateur observers with backyard telescopes, then anyone who knew where to look on a clear December night and remembered how that corner of the sky usually burned. The star was still there. It was simply less itself than it had ever been observed to be. That drop, a 35% reduction in visible brightness, placed Betelgeuse far outside the range of its known behavior. The star varies. It has always varied. Every red supergiant does, its outer layers slowly swelling and contracting in rhythms that span months or years, its surface churning with convection cells large enough to encompass the inner solar system. A certain amount of brightening and fading is simply what such a star does, quietly and without consequence, across the span of a human life. What happened in 2019 was something else, something that had not been captured before, not in the century-long archive of brightness measurements kept by patient observers across generations, not in the records of any living astronomer. The star fell below a floor that had always held, and no one was immediately certain why. What followed was months of careful watching, telescopes on the ground turned toward Orion, instruments in orbit adjusted their attention. Brightness readings accumulated, night by night, as the dimming reached its deepest point in February of 2020, and then, slowly, the star began to recover. It did not explode. No pulse of neutrinos arrived at underground detectors. No ripple passed through the gravitational wave instruments that would have announced a stellar core collapsing inward. The star had simply dimmed, and then over months grown bright again. By late 2020, it was behaving almost normally, and the question of what had happened settled gradually into something that science could work with, a record of light and darkness that researchers would spend years interpreting. The answer, when it came, was stranger and more physical than almost anyone had initially supposed. Something had erupted from the star's surface, not an explosion in any ordinary sense, nothing that destroyed or fundamentally altered the star, but a vast outward surge of material, a mass ejection from the stellar photosphere, unlike anything previously documented in a red supergiant. The event released material roughly equivalent to several times the mass of the moon, pushed outward from the star's surface at around 35 kilometers per second. That is fast by ordinary standards. Against the scale of what Betelgeuse is, it is closer to a slow exhalation, material peeling away from a surface so large that even rapid motion seems gradual when measured against the star's diameter. The ejected cloud moved outward into the space surrounding the star, expanding and thinning as it went, and then it cooled, at a sufficient distance from the photosphere, and below a temperature of roughly 1500 Kelvin, the conditions within the cloud shifted. Gas that had been too hot to form solid particles began to condense. Silicate minerals, the same basic mineral family as the rocks underfoot on any ordinary hillside, began to crystallize out of the cooling stellar gas as microscopic grains of dust. They were invisible to the naked eye individually. Together, as a cloud, they blocked light. The dust formed preferentially over one region of Betelgeuse's visible face, concentrated in the southern hemisphere of the star's disk, as seen from Earth, and the combined effect of that localized obscuration was a dramatic and asymmetric dimming, the star appearing not merely fainter, but visibly lopsided in high-resolution images taken during the event. The research that eventually traced this sequence, published in 22, drawing on ultraviolet and optical observations from the Hubble Space Telescope, described it as a surface mass ejection, a category of event previously associated mostly with the Sun, scaled up to a degree that made solar equivalence seem modest. The Sun has surface mass ejections regularly. They are measured in billions of tons and travel through the solar system as expanding bubbles of magnetized plasma. What happened at Betelgeuse was a surface mass ejection carrying millions of times that mass. The scale difference is the kind that resists simple comparison and asks to be held quietly instead, as one holds the image of a mountain beside a grain of sand, knowing the comparison is accurate and letting that be sufficient. There is a deep strangeness in watching something so large behave in a way that is, at root, familiar. A surface erupts, material flies outward, it cools, dust forms, light is blocked. Every step in that sequence is physically ordinary. The same processes occur, in small versions, in laboratories and in the sky over the Sun. What makes the Betelgeuse event extraordinary is not the novelty of the physics, but the scale at which entirely ordinary physics operates. The dust grains that briefly dimmed a star visible to every winter skywatcher in the northern hemisphere were made of the same minerals as a piece of granite. The ejection that produced them followed the same basic principles as a bubble of plasma leaving the Sun's surface on an ordinary Tuesday morning. Only the numbers were different. Only the distances and masses and temperatures existed at a scale that makes the event feel like it belongs to a different category of reality entirely, which, in some important sense, it does. Betelgeuse's variability does not begin and end with the Great Dimming. The dimming was the most dramatic moment in a century of recorded fluctuation, but the star was variable long before 2019 and will be variable long after. Its brightness oscillates on at least two overlapping rhythms, each with its own physical cause and its own timescale. The shorter of the two runs roughly 400 days, a primary pulsation in which the star's outer envelope swells slowly outward and then subsides, the whole structure contracting and expanding like a breath taken on a geological scale. 400 days is longer than an Earth year. The star completes fewer than 9 such cycles in a decade, and yet against the backdrop of a stellar lifetime measured in millions of years, 400 days is a fast rhythm, a quick, shallow oscillation compared to the longer pulse that underlies it. The longer period runs approximately 2,100 days. That is nearly 6 Earth years, from one peak to the next. Its physical origin is still discussed among researchers. The best current picture connects it to a deep oscillation of some kind, possibly related to the enormous convective motions within the star's interior, but the full mechanism has not been settled. What is known is that the two periods overlay each other in the star's observed brightness record, interfering, reinforcing, drifting in and out of phase, so that Betelgeuse's light curve resembles not the clean, repeating arc of a mechanical oscillator, but something more like two slow waves crossing the same body of water from different directions, their peaks and troughs combining unpredictably, the surface never quite repeating the same shape twice. It is this double rhythm that makes the star feel, when observed over long periods, like something alive in the loose sense that word carries when applied to large complex systems, not alive in any biological sense, not moving with intention or awareness, but varying in the way that a river varies, never the same twice, always bounded by the same banks and always flowing in the same general direction, but different every hour in the small details of its surface. The archive of Betelgeuse's brightness did not begin in 2019. It did not begin in the era of modern astronomy or digital photometry. It began in the latter part of the 19th century in notebooks kept by observers who looked at the sky as a profession or a devotion, recording what they saw with the instruments available to them, sometimes a telescope, sometimes a trained eye, comparing the target star's brightness to nearby reference stars of known magnitude. The American Association of Variable Star Observers has maintained a continuous record of variable star brightness that now stretches back more than a century, built observation by observation from thousands of individual contributors whose names are mostly unknown to anyone outside their local communities. Farmers who noticed stars, teachers who kept logbooks, retired engineers who set up telescopes in suburban gardens and submitted measurements to a central archive that accumulated them into a resource no single institution could have built alone. This is how science sometimes works in the long stretches between dramatic events. Quietly, accumulation by accumulation. One night's measurement laid beside the previous night's, neither one significant in isolation, both of them adding another thin layer to a record that eventually becomes capable of showing something no single observation could reveal. The 2019 dimming of Betelgeuse was recognizable as extraordinary precisely because that archive existed. Without a century of brightness measurements to compare against, the dimming would have been a fact. The star is currently at this brightness. Without context, without significance, without the ability to say this has not happened before, not in any observation any person has made. The archive gave the event its meaning. The meaning was built not in a single year of watching, but across generations of patient attention. There is something worth resting in about that. The astronomers who submitted observations to that archive in 1920 did not know what those observations would eventually help to understand. They were recording a brightness value on a particular night because they found the sky interesting and the act of careful looking satisfying, and because an organization existed that would receive their data and add it to a growing collection. They could not have anticipated that nearly 100 years later, a graduate student at a major observatory would open a database and pull their measurements to use as a baseline against which something remarkable was unfolding. The long patience of accumulated observation connects people across generations in a way that no single discovery ever quite manages. A person who dies without knowing the answer still contributed the material from which the answer was eventually assembled. Betelgeuse is not the only red supergiant that varies. It is simply the nearest, and therefore the best studied, and therefore the one whose variability has entered the public imagination. Across the galaxy, thousands of red supergiants pulse and swell and shed material into the space around them, their light curves recorded now by automated sky surveys that sweep the sky every clear night and compare each star's current brightness to every previous measurement in the database. The scale of this monitoring has changed enormously in the last few decades. What once required a dedicated observer at a telescope, submitting measurements one night at a time, is now accomplished by survey instruments that process millions of stellar brightness measurements per observing session without any human involvement beyond the software that flags anomalies for review. The sky is being watched constantly by instruments that do not tire and do not sleep, logging the slow respiration of hundreds of thousands of variable stars as a continuous stream of data. And within that stream, among the red supergiants and hypergiants, the pattern of variability tells its own story about what is happening inside these enormous objects. A star that varies semi-regularly over periods of hundreds to thousands of days is a star whose outer envelope is in motion, driven by convective cells rising and falling through its interior. The unevenness of the variation, the way the periods drift, the way one cycle differs from the next, reflects the fundamental irregularity of convection at this scale. These are not the smooth clockwork oscillations of a Cepheid variable, in which a specific physical mechanism drives the star into a regular cycle as reliably as a pendulum. The pulsation of a red supergiant is closer to the motion of water in a slowly heated pot, structured, energetic, repeating in a general way, but not predictable in its details, because the underlying process is turbulent rather than mechanical. The largest of these objects, the hypergiants, the stars that press against and sometimes exceed 2,000 solar radii, vary on the longest timescales and with the least predictability. They are the most extreme versions of a class of objects that are themselves extreme by any ordinary stellar measure. Stars like VY Canis Majoris, embedded in a thick shell of ejected material that glows warmly in infrared wavelengths, vary in brightness as material moves through and around their circumstellar envelopes, as dust forms and disperses, as the photosphere itself shifts across a range that would constitute a large fraction of a solar radius in a smaller star, but amounts to tens or hundreds of solar radii here. The boundaries of these objects are genuinely uncertain, not because the measurements are poor, but because the boundary itself is not a fixed thing. The photosphere of a red supergiant is not a surface in any ordinary sense. On Earth, the word surface implies a definite edge, the place where solid meets air, where liquid meets atmosphere, where one material ends and another begins. The photosphere of a cool red supergiant has no such clarity. It is defined, formally, as the layer at which light escapes freely from the stellar gas, the depth where the gas becomes transparent enough for photons to travel outward without being immediately absorbed and re-emitted. But this transition from opaque to transparent does not happen at a single altitude. It is spread across a zone that in the largest supergiants extends across hundreds of solar radii, a diffuse layered region where the density of gas falls gradually from values too high for light to pass through to values too low for light to be meaningfully blocked. The photosphere is not a surface but a gradient, a slow fade from stellar interior to stellar sky. And beyond the photosphere, the star does not simply end. Outward from that diffuse visible boundary stretches the chromosphere, a region of hotter, thinner gas that extends further still. Beyond that, the stellar wind, the slow, continuous outflow of gas driven by radiation pressure on dust grains forming within it, carries material outward for light years, gradually thinning into the surrounding interstellar medium. The circumstellar envelope of a star like VY Canis Majoris or Stephenson 218 is enormous by any scale used to measure stellar objects. The dust within it, warm, infrared glowing, invisible to the unaided eye, represents centuries or millennia of accumulated mass loss, the patient erosion of a stellar surface that will eventually consume a significant fraction of the star's total mass before the core finally collapses. Where, in this layered structure, does the star end? There is no clean answer. The number given when astronomers quote the radius of a red supergiant, the value in solar radii that appears in papers and databases and popular accounts, is a measurement of the photosphere at a particular wavelength of light. But the same star, measured in a different wavelength, or measured with instruments sensitive to its circumstellar dust, rather than its photospheric gas, can return a different radius, sometimes tens of solar radii different, sometimes hundreds. The star is not lying about its size. It simply has no single size. It is a nested set of structures, each with its own characteristic radius, each real, each measurable, each giving a different number, and none of them wrong. This is one of the deepest things about the largest stars in the universe. They resist the desire for precision, not because the measurements are inadequate, but because the objects themselves are genuinely, physically imprecise. They are systems rather than bodies. The boundary is not a closed line, but an open, fading region, gas and dust and radiation intermingled in a zone that shades from stellar to interstellar across a distance that, if it were empty space, light would take several hours to cross. There is a quietness in accepting that. The urge to draw a clean circle around a thing, to say this is where it begins and this is where it ends, is a deeply human one. It is useful for most purposes. It allows measurements and comparisons and the construction of databases in which each object has a defined radius that can be listed and sorted and compared to the radii of other objects. But at the extreme edges of stellar physics, at the scale of red hypergiants, whose outer layers have been continuously losing mass for tens of thousands of years, the clean circle does not quite hold. The object extends, and the extension fades, and somewhere in the fading it becomes indistinguishable from what is around it, and there is no edge to point to, only a gradual dissolution into surrounding space. The stars whose light records are kept in the long archives of variable star observers are in this sense more honest than their listed measurements suggest. Each brightness reading in that century-long database is a single number, a value on a scale that allows comparison, but the star it describes is a layered, shifting, breathing structure that no single number fully captures. The number is useful, the star exceeds it. That is not a failure of measurement, it is a property of the star. Betelgeuse on a clear winter night is an orange point of light at the shoulder of a hunter's figure made of stars. It has been given that position in human imaginations for longer than written records, extend named and placed and incorporated into stories whose origins are now impossible to trace. The orange color is real. It reflects the star's surface temperature, roughly 3,500 Kelvin, cool by stellar standards, the kind of temperature that produces light at the red end of the visible spectrum. What the eye cannot see from that distance of roughly 700 light years is the scale of the thing that produces the light, a sphere whose radius, on the conservative end of estimates, would extend from the Sun past the orbit of Mars, swallowing Mercury and Venus and Earth and their entire histories of oceans and seasons and life in the process. 700 light years is far enough that the light arriving tonight left the star roughly 7 centuries ago. The star as it exists right now, in whatever condition it currently occupies along its evolutionary path, is unknown. The dimming of 2019 and 2020 is old news by the time that light reaches an observatory. The recovery that followed is old news. Whatever the star has done in the past 7 centuries, whatever pulses it has completed, whatever mass it has shed, whatever changes have accumulated in its photosphere and its circumstellar shell, all of that is still in transit, approaching at the speed of light, not yet arrived. This is an ordinary fact of stellar astronomy. Every star in the sky is seen as it was, not as it is. But with Betelgeuse, because of the possibility that this star will eventually exhaust its remaining nuclear fuel and collapse, the temporal gap carries a particular quality of attention. Researchers who work on red supergiant evolution have pointed out that when Betelgeuse does collapse, not imminently by any measure available, with current estimates suggesting tens of thousands of years at minimum before core exhaustion, for though uncertainty in these estimates spans a very wide range, the light from that event will travel outward at the speed of light and arrive at Earth to produce a brightness in the night sky that historical records describe as potentially visible in daylight. That event, if it has already occurred, is approaching. If it has not yet occurred, the star is still out there in its current configuration, pulsing on its 400-day rhythm, shedding gas and dust at tens of kilometers per second, its photosphere hanging in space as a diffuse orange gradient with no clean edge. The archive continues. Each clear night, the automated surveys log Betelgeuse's brightness alongside the brightness of hundreds of thousands of other variable stars. Each value is compared against the accumulated history of the same star on the same night a year ago and a decade ago, and as far back as the records extend. The software that does this comparison does not have any relationship to the star. It processes a number and compares it to previous numbers and flags anything outside the expected range. But the flag, when it appears, reaches a human being who does have a relationship to the star, someone who has spent years learning what its variability patterns look like, who can distinguish the deep periodicity of its pulsation cycle from the kind of surface event that produced the great dimming, who carries in their memory not just a number, but a picture of how this particular object behaves over time. That knowledge was built slowly. It was built by accumulation, one measurement at a time, one clear night at a time, across careers and across generations, in the same patient way that the star itself was built. Slowly, from gas and gravity and nuclear fire over millions of years. There is a kind of symmetry in that. Not a planned one, not a symmetry that anyone arranged, simply the coincidence that the scale on which a star builds itself, slow, gradual, cumulative, is echoed in the scale on which human observation builds the knowledge of the star. Neither process has a goal. Neither knows it is building anything. The carbon and hydrogen that fell together to form Betelgeuse were not trying to become a red supergiant. The observers who submitted brightness measurements to the archive in 1930 were not trying to establish a baseline for a dimming event 90 years later. Both processes simply proceeded, each according to its nature, and the result of one is the star, and the result of the other is the knowledge of the star, and both continue. The circumstellar shell around a red hypergiant carries in its structure the entire history of the star's mass loss. Each pulse of ejected material represented by a thin shell of gas and dust, slightly denser than the surrounding medium, moving outward at whatever speed it was launched. Over thousands of years, these shells accumulate into a complex nested structure that an astronomer reading it carefully can use to reconstruct, roughly, the timing and intensity of the mass loss episodes that produced it. The record is not perfect. Shells interact. Faster material catches slower material from an earlier ejection. Turbulence within the outflowing gas mixes layers that were once distinct. But the broad history is legible, written in infrared light and radio emission, available to any instrument sensitive enough to read it. The star writes its autobiography in its own discarded material. That material drifts outward for thousands of years after the event that produced it. It becomes part of the circumstellar medium, gradually thinning and cooling, eventually merging with the interstellar medium that surrounds it. The atoms within it, oxygen, carbon, silicon, magnesium, the products of the star's own nuclear burning, mixed with hydrogen and helium from its outer envelope, join the broader population of atoms drifting through the space between stars. Some fraction of them will eventually be incorporated into a molecular cloud. The molecular cloud may, under the right conditions, collapse. A new generation of stars may form from it, some of them small and quiet, some of them large enough to become red supergiants in their own time, some of them surrounded eventually by planets made partly from the recycled material of the star that existed here before. This is not a cycle in the sense of a circle that returns to the same point. It is a cycle in the sense of a pattern that repeats without being identical, each iteration different from the last, each generation of stars enriched in heavy elements beyond the previous one, the medium from which stars form slowly evolving over billions of years, as the accumulated output of generations of stellar nuclear burning accumulates in it. The atoms that will eventually form the next red supergiant to occupy this region of the galaxy are drifting now, some of them in the expanding shell around a star that still shines. There is nowhere in this process where the material stops and rests. It is always in motion, from the photosphere into the circumstellar shell, from the shell into the interstellar medium, from the medium into a collapsing cloud, from the cloud into a new star. The motion is slow by human standards. A shell of material expanding at 30 kilometers per second takes thousands of years to reach the nearest neighboring stars. A molecular cloud takes millions of years to collapse into the next generation of stellar bodies. The timescale is not human. It is stellar, measured in the lifetimes of the objects involved, which are measured in millions and billions of years. Against that timescale, the few months of the Great Dimming are brief. The century of brightness records that allowed the event to be recognized as extraordinary is brief. The entire span of human civilization is brief. Even the main sequence lifetime of Betelgeuse, the several million years it spent fusing hydrogen in its core before expanding into the red supergiant it now is brief against the age of the galaxy in which it formed. None of this makes the event small. The duration of a thing and its significance are not the same. A few months of dimming, observed by thousands of people who looked up at a familiar constellation and noticed something different, preserved in databases and published in papers and discussed in languages that did not exist when the light now arriving in telescopes first left the star. That is not a small thing, whatever the time scale on which the star itself operates. The event was real, the watching was real. The knowledge built from it is real and will persist, and the star is still there. On a winter night in the northern hemisphere, when Orion rises in the east and climbs slowly toward the meridian, Betelgeuse sits at the hunter's shoulder with its orange light unchanged to the naked eye from any other winter. The great dimming has passed. The surface mass ejection that produced it has long since expanded beyond the photosphere and cooled into dust and thinned into the surrounding medium. The circumstellar shell is slightly larger than it was 5 years ago, by a margin so small that only the most sensitive instruments could detect it. The star pulses on, swelling and subsiding on its 400-day rhythm, with the longer 2,000-day cycle slowly rising or falling beneath it, the combined effect producing a brightness that will continue to vary, sometimes by a little, sometimes perhaps by more, as long as the star exists. The brightness record grows one night at a time. Each clear winter night adds another measurement. Each measurement is compared to the measurements before it and stored alongside them in an archive that will outlast every person currently contributing to it.